future because I don't have these chapters. Okay. So on chapter 5.
Chapter 6, right?
Chapter 6, sorry. We're on chapter 6. We went through chapter 5 PowerPoint. We're on chapter 6. I know where we're at. So we all know old hardwired controls all used control relays. Okay. We've studied that in the last class, motor control. And the whole purpose was designed to replace those relays. Okay. Now, I'm not going to spend a lot of time on this because we beat this to death in motor control, okay, in this PLC class. But we're going to kind of skim through it. So we know what normally open and normally closed mean, right?
Yes.
All right. We got some relay symbols. What we're trying to do is we're trying to get into more of the conversion from hardwired control systems to, I like to use the term software in the relationship. They're pretty similar, but there are a few differences. Here we have an internal relay, B3, :1/0. We have an internal relay. Now, any bit we can make an internal relay bit. And so it's just a stand-in that we can use right here. You with me? We don't have to use actual inputs and outputs. We can program virtual bits. Here we have contactors. We have motor starters. I want you to pay attention. We talked about overloads and feedback. If you're going to wire a contactor to a PLC, eventually it's going to trip. It'd be nice if the PLC knew that. Depending on the operation. If it's a linear conveyor system and you've got conveyors 1 through 10 and number 5 trips, what happens? And it's a big mess. So down here on the overload relays, there's a couple of options. This is supposed to break the neutral down here. You got a normally closed and normally open. They always put the normally closed, that's for your PLC feedback right here. These two, this normally open would break the neutral. I'm sorry, that's normally closed. It's hard to see on there. Anyway, the normally closed would be where the neutral went to break the neutral to shut it off, and normally open would be feedback. Sometimes, depending on the contactor, they'll put them up here too. Here's an extra normally open. Remember, we don't have to have a latching circuit. It's in the PLC. Right. Here we have old hardwired system. Here we have an equivalent. Notice they put the stop button in front. I don't do that. I always put my stop button in the back. Doesn't matter. It's going to work the same, but that's what I did. Push buttons. We have our standard normally open, normally closed. How do we program a normally closed stop button if we would like to have positive logic? We program it normally open. We have a selector switch. Notice the different positions here. Hand off auto. I'm going to be honest with you. Push buttons are pretty much going away on control systems. Only thing we got to keep is some kind of OSHA approved hardwired e-stop, dual contact now. It does have an electronic component, most of them, an e-stop relay. But why do we want to spend money on button when we can just have a 10-inch touchscreen? And if we don't like a button, we throw it away and make a new one. It doesn't make any sense. Anybody seen some of the old control systems before touchscreens or human machine interface? The amount of buttons on it, there'd be like 100 buttons on the panel. You'd have to pay that. You'd have to pay somebody to wire it, knock all the holes in, or you can put a nice clean little 10-inch hole and stick a touchscreen in there. If you're worried about control systems going out, you know, well, if my touchscreen goes out, well, put 2 touchscreens on it. Or, like everybody else, buy a spare touchscreen and put it into stock. All you gotta do is load a program that'll work anywhere in the plant. Standardized. Dip switches. A lot of our PLC cards will have configuration. Some of them, analog cards, if you wanted to have voltage input or current input or current output, sometimes you have to flip a dip switch. So, what if I don't know if I've said this before, but what's your number one friend when it comes to automation? Google. If you don't, if you're putting in a card and you've never done it before, Google and read the manual and see what it says. Anymore, all the manufacturers, they get tired of printing paper and it's an added cost and everybody just throws the box away anyway. A lot of times you don't even get the manuals anymore in paper format. You're going to have to use the Google. Here we have an example of limit switches, normally open, normally closed. Now I'm going to be honest with you. We've talked about this before. Most all of your sensors and limit switches, they're going to all come with a normally open and normally closed set of contacts. Even your photo eyes. It may not be contacts. But if you hook up a photo eye and it doesn't work the way you think it should, or it's already programmed and it's working backwards now, just go flip the wires on the photo eye. It's got a, they all come with a normally open and normally closed set of contacts in them. Here's temperature switches. They're basically the same thing, limit switch. Pressure switches. They're all going to come with a normally open or normally closed set of contacts, mostly. Level switches, same deal. Here we have sensors. What's the square mean around a limit switch? And what's that square mean when you see that? That diamond. The diamond. Totally forgot. I heard that. That means it's a semiconductor. It's an electronic switch of some sort. And it's got the little diamond around it. The same thing goes for a photo eye. This photo eye has little rays coming in. But here's how a proximity sensor works. Puts out a little field. You can get them. You can get proximity buttons to replace. You have a. We used to put them on machines. You know, the buttons would get cycled maybe, I don't know, 5,000 or 6,000 times a night. Well, that doesn't last long for a button. Plus, the operator has to. It's more hard. It's harder on the operator to push in on a button than it is just to touch a square. So we would replace those buttons with proxies. All they got to do is touch them. They have different types of sensors. Now, a 3-wire sensor, you got a hot, some kind of ground, and then a signal, right? Well, typically a 2-wire sensor, they're not very big. And I'll tell you why. Because they actually work that you don't see it, but power comes in here, and then the little sensor uses just enough and bleeds it off. This would be a PLC input right here. Are you with me? It bleeds it off. Here's the PLC input right here. And it's just enough to make the sensor function, but not enough to trip the PLC input. Does that make sense? So they do transmit a little power at all times because they've got to keep the sensor powered up. I've had a lot of problems with these in the past, so, but it just depends on what you got. Those are typically a little cheaper. Proximity sensors have a sensing range. Where are you going to find the sensing range of a proximity sensor?
On the box, it should be on the label.
Should be. You're going to find it on the Google. It should be stamped on there, but we all know Sometimes they're hard to make out. Sometimes it's just a number in the part number. So you're going to look it up in the manual of the sensor. This talks about our leakage current that we talked about. This talks about how they can work off plastic. You can have stuff that sense plastic. You can have stuff that sense metal. You can get color sensing photo eyes with the teach button. Let's say you've got a label on a product and you want to make sure that label's on there. Well, you teach it you adjust the sensor to teach it a color on the label. Maybe it's got a blue spot on it. So you adjust your photo eye to always, every time the product went by, it would go by that blue spot on the label and have it adjust. And if it ever had let product go by, there wasn't a blue spot, then it would sound an alarm and kick it off. Usually that's a kickoff, so that's it wouldn't ever stop production. It'd just kick off the bottles that didn't get the label, right?
A proximity switch, do they work off of magnets also?
Well,
The reason I ask that because that's what we had on slide gates out on the matrix plant.
you're thinking about,
If it gets very close, then it detects, when it gets close enough, it detects it.
well, they do have, they sense electromagnetic fields. They put off one. They do have sensors that have magnets on them, a magnetic reed switch. They have those. Typically, you see them on air cylinders. Basically, on the backside of an air cylinder, hydraulic cylinder, there will be a magnet inside there, and the little sensor will be adjustable up and down the entire length of the cylinder. And so when it sees the magnet in the back inside there, it knows it.
It tells that it's either closed or
Yeah.
it's either open, yes.
So here we're just talking about different capacitive proxies. Here's your magnetic reed switch right here. Okay. Anybody ever owned a BlackBerry phone before? You know what their big deal is? I had one. I liked it. You know, after Android, it kind of went out of fashion. But the big deal about those is you buy the BlackBerry case and you save so much battery life because whenever you put your phone in your case, the screen's still on. With a BlackBerry in a BlackBerry case, it has a magnetic sensor in there. So when you put the phone in the case, it knows it and automatically turns the screen off. You'd be surprised how long the battery
Pull
lasts.
it out.
It automatically comes on. You don't have to hit no buttons. You just put it in, it goes off. Pull it out, it comes on.
Never had that case.
Here we have light cells, etc. Here we have a photo op. Here's where I was talking about. This has a transmitter receiver, okay, right through here. So it's a little bit more accurate. With these diffuse photo eyes, they'll depending on what you're trying to detect. I'll give you an example. The worst thing is whenever you have a product on a palletizing line and you put the shrink wrap around it. Well, it's shiny, right? Well, it'll throw off diffuse photo eyes because they start getting confused with that shiny package and they'll start flickering. Okay, or maybe one time you're running a white box and then the next time you're running a black box. They don't like black. They don't like black at all. Okay, most of the time if you had a packaging line and you went to a black box, you would pretty much have to either go back to a brown box or shut it off.
That would count like 125 trays with 10 seconds.
Yeah,
They start running black tray, or you go over and just
yeah.
fine tune it to get count.
So that depends on how much light can get reflected. We all know that the whole reason we see white is because it reflects more light, right? Black absorbs. Now, we also have retroreflective. We looked at those. We hooked those up. They got a little reflector in there. Okay. We also, a lot of our photo eyes can either be light operated or dark operated or both, depending on the setting. Light operated, as the name suggests, when the light shoots out and bounces back some way, or it's sent in, it activates. When it's dark operated, it activates when it doesn't see the light come back. Now, why would we want to have a dark operated photo eye? In this instance with a reflector.
Scary light.
Well,
You did that at counter, too.
yeah, but here's the deal. If this was on a packaging line running a lot of boxes and it was dark operated, then when the box fell off and knocked this reflector off, the system would know that either there's a package in the way or the reflector got broken or knocked off. Does that make sense? And then it would shut off appropriately. If this was light operated, it would work backwards, and if it knocked off the reflector, it would know. Make sense? They have fiber optic adapters for all of these. It's your standard photo eye. You buy the little thing, and it comes in, and you just snap it on the front, and it's for it's a way to take a diffuse photo eye and make it a pinpoint, basically. Barcode scanners, we talked about that. Told you about string variables and how you pull in the data into a string. Ultrasonic sensors, we hooked that up. It's an analog. Remember when we hooked up the ultrasonic sensor, 4 to 20 milliamp signal, and we put our hand in front of it, signal went up and down. We have those on our PID trainers. Hopefully we'll get time, we'll get on those and you'll see it work. Strain gauge. Load cells. Load cells typically use microvolts. So when you get a load cell, it's going to go to, they use microvolts. Basically, it's a semiconducting material that whenever you bend it or stretch it, it's like a metal, it produces a small amount of voltage. And then we read that with some kind of transmitter that's close to the load cell because we get a voltage drop, right? So we gotta have it close. There's a listing in them, and they gotta be within 2 or 3 foot. And then we change that over to probably a 4 to 20 milliamp signal and send it onto our PLC. Thermocouples, they work the same way. There's not much difference in how a strain gauge and a thermocouple work, except one's activated by heat, one's activated by pressure. Flow measurement. We have paddle wheels, pulses. Most everybody, they're a little bit more pricey, but like a Venturi effect. Remember the Venturi effect from fluid power? When you gently restrict fluid flow, we get a pressure drop in the middle. Well, they sell Venturi meters because depending if that was acid right there, that paddle wheel would go away before long, it would dissolve. With a Venturi effect, we tell it what the specific gravity of the water is and the diameter of the pipe. And then the little magic box, the little sensor on top will tell us the gallons per minute or whatever we want to display it in and transmit that to a signal back to the PLC. Some of these are even on their own little network. They have like a little network. You can actually reprogram them on the computer. So they send a signal transmitter to, or you could go out there and hook onto the signal line and actually it's called a Hall effect. It's a Hall something network. I don't remember. But anyway, there's actually you hook up a laptop to these and program them. Tacks do pulses. Okay, encoders and tacks, just a different way to do it. This is the same thing as in your old ball mouse, right? The one you always have to take off and clean out so it work again. We have different outputs, coils, relays, pilot lights, alarms. These are another symbol for heater. Of course, you wouldn't hook a heater to a PLC. That would go to a contactor. Solenoid, possibly. Horns, most definitely. Here's an example of an actuator. Here's a little solenoid and a coil, and it just pulls this in and out. Solenoid valves, I mean, we beat this to death, so I'm just flashing it up there. You've already had this in previous classes. Stepper motors. Yeah, you know, stepper motors are basically every revolution is divided into a number of steps. And some of them have a little control board, but basically you send them a number of pulses and they'll rotate an X number of times. Now, there's no feedback on a lot of them. They're not very accurate. There's not an infinite range. They're going to go, you know, when you get a stepper motor, you say, well, how many steps do it have? It's got 180. That means in a 360-degree circle, it can move 180 places. It's got 360. Typically, these are all in printers. Everything, you know, you want a home printer. That's what feeds the paper to move it through. That's how the printer knows when the paper's shifted to print the next line, etc. Servo motors. They have amplifiers. They'll have a tack on the back and a feedback device and probably a separate controller. The PLC will just communicate with that controller and it'll tell it a position to the servo controller, and then the servo controller magically moves it there and tells it, yes, I am in position, do your thing. Talked about seal-in circuits. Got start, stop. Now, here's my memory or my latch. We've replaced that. You've already done that. What did we replace it with in your examples of seal-in? We replaced it with the output. We programmed an output as an input and replaced it. So there's no physical connection there anymore. Most control systems, we talked about feedback from the contactor. That'll just be for alarming. There'll be an alarm bit in there. You'll probably still use the seal-in because there is a time delay, mechanical action time delay from when you fire an output. And the PLC will pick that up and you'll get false alarms. So basically what you'll do is you'll tell the motor to latch in maybe for half a second. And then if the motor's been told to latch in and you don't get feedback within half a second, you'll sound an alarm and shut the motor down. Latching relays. Seal-ins. Same thing as latch. Well, we don't have to actually have a seal-in. Before, on an OTE instruction, we've simply been telling it to activate, and it puts a 1 in there. When we don't activate it, when the logic to the left of it becomes false, it goes off. But we have a latch instruction and an unlatch instruction. Typically speaking, if you have a latch instruction, you're going to have an unlatch instruction somewhere. Before, an OTE instruction had infinite, or you can only use it once, right? If you try to program it more than once, you got errors. Here, we can program these as many times as we want to. However, if you do that, especially for motor control, what you'll find is either you screwed up or somebody else screwed up, and you've got this motor latching and unlatching 100 times, and you tell it to come on one time, and you're not paying attention to the logic that's 30 rungs below, and then something happens and it turns it off, and you can't figure it out. So if you take your program and you don't use these for motor control, you just use a seal-in circuit, in our previous example, then you'll know where to look if the motor's not coming on or going off too soon. If you have 100 of these, you have 100 latches, you got 100 places to check for where it's screwed up. You get me? Now, you can latch bits to say conditions happen and to make sure something happens, and when something happens, unlatch it. That's a great job for it. But I would never latch just an output motor starter. Just always leads to problems. But you can. Here we have an output. We've latched and unlatched. We latch the motor on and we unlatch the motor off. Here's our start button. Here's our stop button right up here, on and off. Here's start. Here's stop. Now, you want to see the latch being used? Let me pull that up on the, let's fire up the PLC program. Fire up RF Logix 500 and we'll look at it. It's pretty simple. Here we have a standard motor control, or we can just reprogram that with a latch. Oh. When we do it this way, guess what? We got to flip the logic on the stop button. It's wired normally closed. Stop button's pulled out. We hit the start button. Then we kill power to the stop button, and it goes off. Push in the start button, it latches the motor, then we kill power to the stop button, and it goes off. One thing about these is, let's see if we can do this. I think you can toggle these bits from the PLC. So you can't, you don't have to do a force. If I want to see one come on, I just toggle it. If there's nothing telling it to go back off, it will stay off. If I push in the stop button here, there's my stop button. Now I can't toggle this. But I'm telling you, that's just not a good idea to use that for motor control. Here's an example of a program used to control the water level. Now let's kind of break this down. This is kind of the meat of this whole section. We're getting to it. I believe we'll take a break here shortly.
Different today. It looks a lot different today than they have.
Yeah, we're going to take a break. We'll be through this in just a second, but let's break this down because I'm broadcasting right now and I can't hardly pause it. That's one of the deals. We're going to get through this and then we'll take a break. So here's two conditions. First of all, these are bits that don't really exist. Two conditions. Well, I guess it does have a manual auto switch, but we're either in manual or we're in auto, right? So this says when we're not in auto, we're going to look, hold on a second. I always get this one backwards. Let's see. All right, so when it's closed, when this is true, it's an auto, okay? And so when it's in manual and the low sensor switch, which means I've got water in there, then I can turn the motor on and off. When I'm in auto, I'm going to look at this latch unlatch bit, which is down here. So when I'm in auto mode, I'm going to come over here and monitor the high sensor. The tank is full, and I'm going to latch. Are you with me so far? I don't know if I like this example, but so I'm still in auto mode. I've latched. My on switch is on. I'm going to run the motor and empty the tank. Remember what we're doing? We got a high sensor, low sensor, on and off switch, and manual auto, and then a pump motor. So that's all we're going to do. So we're still in automatic mode. And when it sees the low switch not on, it's going to unlatch it, shutting off, because we're down here. The water level's down here. We got to shut it off. And that's how it works in the automatic mode. And then down here with the indicator lights, I simply just tied them into the motor and the sensor and the high sensor switch. Here's showing I/O connections for that example. I really don't like the descriptions here because whenever I do a manual auto switch, I'll put a big description that says when switch has a bit of 1, it's an automatic mode. If it is equal to 0, it's in manual mode, because it gets really confusing when you put manual/auto right there. Which is the manual, which is the auto. Well, you design that in your descriptions. So here we go. We're going to convert some logic, hardwire logic, over to the PLC. Here we have a filling and capping. The tasks are fill the bottle and press the cap on, right? Fill the bottle and press the cap on. What are we going to do?
Fill them on.
How many times are we going to do it?
As many times as it takes.
As many times as it takes. Here we have combination controls that require certain operations to be performed without regard to the order in which they were performed. So what they're saying here is this is sequential, and this is, well, I can slap a label, and then I can slap a label on this side, and I can slap a label on this side. I can do them at the same time. They are not dependent upon one another. However, the first one, I can't put the cap on until I put the liquid in there, right? So they're sequential. Here we have automatic control. This would be like a PID controller, maintaining a set point in a furnace. Here is a sequential process control. Start button is pressed. We're going to push this start button right here. All right. What's the next condition we're checking for after we press the start button? Well, we're making sure the stop's pulled out. Then we're making sure the limit switch is not active. And then we're doing a control relay. And the control relay is the latch circuit going around. All right. And so then we have a CR2 is not on. We're going to fire the stop light. And if we have a CR3 on, we're going to fire the green light. And if we have a CR4 on, we're going to run the motor. Here we have the same deal. We're going to use an internal relay bit. We're going to latch it on. We're going to do the same thing. We're just using an internal relay bit. Here's a jog circuit. Here we show a jog start and stop. Here's the start button. Here's your stop button, internal relay. It latches on. Whenever we hit the jog, we're simply just going to turn the motor on. I don't really like that example. Most of the time, what I would do, if I wanted a jog switch, this is what everybody does. You put a selector switch in there. Just put a selector switch in there.
Yeah.
So it can either go stop start or it can go stop jog, right?
Yeah, hold on. I would much rather see that. Stop button's pulled out. The jog is set to run mode. It works just like a start-stop. I flip it over to jog mode, and now my start button becomes a jog. All I did was break the latch with a selector switch. Those are in those examples I printed out and gave you. You should remember that. We went through that, right? There's one version. I like my version better, but there's one version I give you. I think that's in your book. So I'm not going to go through that because we've already done the garage. This is also in that Logix Pro right here. Continuous. That's the next exercise. Here's continuous filling operation. We've got solenoid, a level switch, and a photo switch. So what we're doing here is we've got a run bit just to say the thing's on. When the run bit's on and it's not level and it's not full and the photo eye gets made, we're going to fire the fill solenoid. All right. When the photo eye is not made or it's full and the run bit's on, we're going to run the conveyor path. So basically what they're saying is it's going to run by, it's going to hit this photo switch. It's going to drop stuff in here until this is level. Once this level switch comes on, we don't look at this photo eye anymore, and we run the box out. That makes sense? That's what that logic's telling us. And that little part about running out is done right here. Here's our solenoid. Here's our motor. So if the photo eye, this right here stops it, it's in run mode, but it's bypassed by the full sensor. Do you see that right here? So it runs up to this photo eye and stops the motor. Remember the run mode right here is just a selector to say I turn the thing on. And so now we're looking at the photo eye. Once it fills up, we bypass looking at the photo eye, we run the box out.